Okay, uh, in this chapter, we're going to be looking at the model selection, of which we're going to be looking at the comprehensive overview of model selection and regularization techniques in linear models, addressing issues like improving the predictive accuracy, interpretability, and controlling of overfitting. So, looking at this chapter, we have some couple of uh, topics to address, which one of them is linear models and motivation to alternatives if we're not using it. So we know that the standard formula for linear models is going to be given as y equals to b naught plus b1 times x1 plus up until bn times xn plus epsilon, which is the error for that particular model. So we know from the equation that we gave above, it actually entails that y is the responsive variable and xi's are predictors and epsilon is the error term like I've mentioned before. So while linear models are simple and interpretable, they can be improved in terms of prediction accuracy and model interpretability by excluding irrelevant predictors. So from the set of variables that we are given as the predictors, we just need to use the ones that are suitable for that particular activity that we're doing. Then we also have what we call a least square, which may lead to high variance in predictions, and alternatives are considered to address these issues. So we also have this. We learned about these three classes of the methods. Then which we know it's a subset selection, stepwise selection, and the last one, which is shrinkage method. So looking at the subset selection, which is identifying the subset of predictors that best fit the model. So we don't need to use everything that is in the data, but the ones that that best fit the model. And it also involves fitting all possible models with different combination of predictors and selecting the best based on the criteria like residual sum of square, which is the error in this case, and cross-validation error. So we're just going to look at the error in general to say of the combination that we did, which one best give us the good result. Then we're going to be looking at the second point here, which is shrinkage method. So regularization, shrinkage method actually deals with regularization. Then this technique fits a model using a predictors but shrink the coefficients towards zero by adding a penalty to the loss function based on the sum of square error. Then this penalty term helps control variance and prevent overfitting but does not perform feature selection. And in this shrinkage as well, we have what we call lasso. Then the lasso is similar to ridge regression but uses L1 regularization, which shrinks some coefficient exactly to zero, effectively performing feature selection along the regularization. Along with the regularization. So moving right along into the last one, which is the dimension reduction, which mostly we use principal component analysis or partial least square. So from the principal component analysis, this principle is applied to reduce the number of predictors to a small set of linear combination of the original predictors. Then you moving to PLS, which is partial least square. It works similar to PCR, but uses response variable to guide the creation of the components, ensuring that the new predictors are not only representative of the original ones, but also predictive of the response. Then we're going to be moving right along to another section that we also learned some stuff in it, which is the best subset and stepwise selection. So in this one, the goal was to identify the best model for each subset size defined by having the smallest residual residual sum of squares, or large of r squared. So a cross-validation prediction error or an information criteria like AIC or BIC is used to select the optimal model size. And looking at the stepwise selection, this may be computational efficiency and may not always find the best model because they explore only a limited subset of all possible models. Then moving right along to the shrinkage method. So the shrinkage method in ridge regression, it optimizes the problem into, like, now we have the tuning parameters controls the shrinkage level with cross validation used to choose the best value. We also gonna look at it from the lasso point of view. Then we see that this forces sum of coefficient to be exactly 0, and we have the formulas that we learned just to see how does that do and perform automatic variable selection. Then moving right along to the other section, which is the dimension reduction. So most of the techniques that are playing role in this is PCR, which is principal component reduction. So in this scenario, the principal component that captures the most variable in the predictors, but this technique uses that to capture the most variable in the predictors, but the components may not necessarily be the most predictive of the response. And we have partial least square, which creates components that maximize the covariance between the predictor and the response, making it a more supervised form of dimension reduction. Then moving right along to model evaluation and selection. So in this scenario, the goal that was emphasized in the model selection is to choose a model with the lowest test error, not just the one with the lowest training error. This distinction is critical because a model with low training error might be overfitting. We also are gonna look at we looked at the cross-validation, and the cross-validation is highlighted as an effective method for estimating estimate test error, ensuring a balance between model complexity and prediction accuracy. Moving right along into the model selection criteria, which we see several model selection criteria are introduced, which we see a CP, which is adjusting error by adding a penalty proportional to the number of predictors. Then we have archaic information criteria, which measure the quality of statistical model for a given data set, penalizing complexity. Then we have Bayesian information criterion, which is similar to the ones that we spoke about, AIC, but impose a stricter penalty on the number of predictors. And the last one in this section, we saw the adjusted R squared, which is the modification of R squared that adjusts for the number of predictors in the model. So we also had some typical example where we also saw how ridge regression and lasso shrinkage pathways evolve as the tuning parameter increases, highlighting how coefficient and shrunk in regression, and selection in lasso. So that is the method that we learned in this chapter, and we've seen that there is a point that is emphasizing that no single method that no single method is universal outperforms the others. The choice depends on the underlying data and relationship between the predictors and responses. Thank you.